My name is Yaqiong. Today's talk is about the Recurrent Dirichlet Belief Network for interpretable dynamic relational data modeling. My supervisor is Associate Professor Lin Chen. First, I will talk about the motivation of this work. So, Dirichlet Belief Network, so-called the DBN, is a very promising interpretable modeling architecture. So, we propose a deep dynamic probabilistic framework based on this model and to study the interpretable hidden structure from dynamic relational data. And so our proposed recurrent DBN have a few advantages. First, it can provide us the interpretable hierarchical latent structure within and across time step. Second, it can provide us the recurrent long-term temporal dependence. This is outperform the one-order Markov description in most of the dynamic probabilistic framework, which is only depends on one step the time. Then this model also can reduce the computational cost, which makes it to scale to the number of positive links only. So I will first give a brief review of the DBN model. In general, the DBN model constructs a multi-stochastic layer architecture to present interpretable latent distribution for objects. So if we apply it to the relational data, so the given data is a binary observer link matrix. So and the Rij denotes whether node I has a relationship to node J. Use the DBN, we can construct a K-length and L layer of the community membership distribution pi for each of the node I. So so the generative process is shown as below. So in order to generate the membership distribution, so the DBN introduces information propagation coefficient beta. So the larger of the value of the beta I prime to I in layer L minus 1, it have a greater value on influence the generation of the pi I in layer L. The xi is the latent count, is the estimator of the pi I. Finally, the DBN used the function of f xi ji to mapping the pi I to the linkage probability. So the inference of the DBN is quite difficult in some of the steps. For example, for the membership distribution pi, it's very difficult to directly implement it because the prior and the posterior of the pi I is not conjugated. In order to address this problem, the DBN give the count information xi for node I, and then the DBN upward propagates xi to all the nodes in the L-1 layer through a Chinese restaurant table distribution, and each node in the L-1 layer collect these propagation accounts and summarize to give to the xi count in the L-1 layer. So when we repeat this one by one, then we can get all the xi count in the hierarchical structure. This will be used to downward sampling the membership distribution. In order to handle the dynamic data, we attach an index t to a variable to denote the corresponding time step. And thus, the observation data is become a 3-dimensional binary data. So where the RIJT denotes where node I has relation to node J at the T time step. So we show below is show the generation process for generation the membership distribution pi. The whole process also shown in this figure in your right hand side above the dash line. So we except only introduce one information propagation coefficient. We introduce two of them. One is the beta, one is gamma. So beta is help to propagate all the information between layers, and gamma is help to propagate all the information between times. Same as before, the greater value of the beta and the gamma will have greater influence between the related membership distribution between time and the layers. Here we just let beta and gamma equals 0 when two nodes don't have relationship. This can help us greatly reduce the computational cost for calculation beta and gamma, which means we only need to calculating the positive links. At the same time, the phi is like the linear summation of the information in the same time in the previous layer and the previous time in the same layer. So when beta value is much greater than gamma value, the hierarchical structure play a more important role. Otherwise, the temporal dependence were more important. So after we get the membership distribution, the relational data can be determined as below. So this process is shown in a figure in your right hand side down the dash line. In this process, so the latent count x can be regarded as an estimator of the pi. This can help us to implement the posterior sampling for latent count x efficiently. At the same time, the RIJT is mapped to the latent Poisson count random variable matrix C. In this case, only the non-zero links are involved when we inference C. This can much reduce the computational cost for calculation C. Regarding the recurrent structure, so like the one order Markov property to describe the temporal dependence, for example, the state at time t only depends on the state at time t minus 1. But in our model, the state at time step t depends on several time steps, which the deeper our structure is, the more time that can involve in this process. For example, if our structure have two layers, then the expectation of the latent count x at the time t depends on both the membership distribution at the t minus 1 and the t minus 2 step. So this structure allowed us to summarize and abstract those random variables, capture both the hierarchical latent structure and the dynamic dependencies. So inference of the our model. So not like unlike the DBN inference process, they using upward propagation latent count and the downsampling membership distribution. So we propose the upward backward propagation latent count and forward downward sampling. The whole process can summarize as in the picture show you right hand side. Here, the count in the count x was directly propagated to the m in the last layer. Then take the count m in the last layer and the last time step in this figure. It will transform to the count y through a Chinese restaurant table distribution. Then y just outpropagate and bypropagate as a and z to the m in the previous time and the previous layer. So after that, in each of the time step, we summarize all the information being passed from previous process. Then we can generate all the M accounts in this structure. Then this account will be used in forward and downward sampling in membership distribution for each node, each point, and at each layer. In order to value the performance of our model, we compare to 9 different methods, including static and dynamic model, and apply those methods with ours to the four real world data. It's very obvious that our model outperforms all the methods we selected. And the more complicated the model structure is, shows higher the AUC number we got. For example, here we already tried different like a different amount of the group. Like we set the k to 10, 20, and 30. So when k equals 30, we show the most of the highest AUC is shown in this setting. We also visualize the latent variable. First, we visualize the hidden membership distribution. So here we can find that doing this so here we visualize 10 time stop and the 3 layers. Then for each we can see how the pattern change during the time and during the layers. For example, for the membership distribution when L equals 3, we could say few time range changes for the membership distribution, like T1, T2, and 3, and from T4 to T10. So which means they changed this 3 period. At the same time, we also visualize the beta and the gamma through the layer and the time. So in the beginning, in the first layer and the first time point, we didn't see. We see the beta and the gamma is quite small because not many information involved in the calculation of this. Since the information, the more information involved, the higher value we get from those numbers. And we can find that in this data set, the hierarchical structure play more important role than the temporal structure, because with the ratio of beta to gamma is always is to around 1.5. So we summarized our paper as below. So in the model side, the recurrence structure are designed to model long-term temporal dependence. Also, the interpretable and organized latent structure are well explored. From the inference side, we develop an efficient Gibbs sampling using the upward, backward propagates and downward, forward sampling. Our results showed significantly improved model performance in real-world dynamic relational model compared to the state-of-art, including better link prediction performance and enhanced interval latent structure visualization. So thanks Center and UTS helped me with the study, and thanks for my supervisor and the co-supervisor Lin Chen and Professor Bingley, and also this work is thank you for the helpful discussion with the Dr. Fan and the Professor Scott, Professor Season in this study. This is the relative reference regarding this talk.
Okay, so any questions from the audience? Oh, okay, if not, maybe we can find speaker and then we can, next speaker can